Swayam Prabha. Digital India. Educated India.
Hello and welcome back to this series of lecture on elements of solar energy conversion. Today here we are at lecture number 26. So, up to the last class what we were doing, we were analyzing the parabolic trough collector. We have finished the part up to which we have derived the useful heat gain by the parabolic trough and the efficiency of the same. Now, here there are few things which are missing, in the sense like we have assumed that this UL or the overall loss coefficient we know that, okay, that is what we assume. But in reality we have to calculate it. How to calculate it? So, we will look at how we can get this overall loss coefficient for a parabolic trough collector. So, here we have to go back to the drawing board, that means we have to find out the thermal circuit again, and then only we will be able to find out this overall loss coefficient. So, here unlike the flat plate collector, we do not have any top loss coefficient or bottom loss coefficient. So, this is a circular tube which is carrying the working fluid, and we have a concentric circular tube of transparent material which acts as the cover. Okay. So, there is no top and bottom, but we have a single loss coefficient which is UL, right. Now, if we look at the heat flux at different levels. So, first one is, so let us say heat flux per unit length, right. So, we are not considering how the heat flux is changing along the length. So, what we are doing, this QL, which is the heat loss divided by L. Okay. Now, if we look at, and this will be the same. So, this will be same between the plate and the cover, or let us say plate, which is basically the absorber tube, okay, not the plate, but just to be consistent with the terminology that we have used for flat plate collector, we are using the same terminology, plate. So, that heat flux between the plate and the cover, okay, will be the same as between the cover and the ambient, right, because the current will be the same as they are series connected. The current will be okay. So, what we can write? We can write first this between the absorber tube and the cover, we can write that the heat transfer coefficient between plate and the cover multiplied by the temperature gradient, which is the mean plate temperature minus the cover temperature. Okay. And the area here we can find out by the outer diameter of the tube, absorber tube, pi d naught, plus this is the convection part. Now, we will have the radiation part as well. So, there we will have this sigma, which is Stephen Boltzmann's constant, pi d naught multiplied by 4th power of mean plate temperature or mean tube temperature minus 4th power of the absolute temperature of the cover, and that will be divided by 1 over epsilon p, which is the emissivity of the plate, multiplied by d naught by d c I. So, this is the cover inner diameter d c I multiplied by 1 over epsilon c, which is the emissivity of the cover, minus 1. Okay. You can use another set of brackets. So, here what we see that due to change in area, because as the diameter changes, the area also changes. That is why we have this factor d naught by d c I, okay, which is not present in case of a flat plate collector. When we have two parallel plates, the area across the heat transfer direction does not change, but here it changes. That is why you have this factor. Now, this Q L by L, the same current flows between the cover and the ambient. Okay. So, there what are the factors? First one is what is happening through the convection. So, we have this term here, this H W is the, we call it wind loss factor. This is nothing but the coefficient of heat transfer due to wind, because cover is losing heat to the ambient because of the wind flow, right, and the other part will be the radiative part, and here we have dCO, that means the outer diameter of the cover tube, multiplied by the emissivity of cover material, multiplied by the 4th power of cover temperature, absolute temperature, minus the effective sky temperature raised to the power 4. Okay. So, this is the same current is flowing, and that is why these two quantities you can equate. That means, this thing will be equal to H P to C T P M minus T C pi d naught plus sigma pi d naught T P M 4 T C to the power 4 divided by 1 over epsilon T d C naught divided by d C I 1 over epsilon C minus 1. Okay. So, these two quantities you can equate and you can find what is the Q L by L. But now the question rises that what are the values of this H P to C or H W. These things we do not know, right, and the typical way of finding out for the flat plate collector will not work here. Why? Because flat plate is a geometry where you have the coefficients available easily, but for the parabolic trough we have these concentric tubes, and the flow over a tube is completely different than flow over the flat plate. That is why we have to use separate coefficient or separate correlations for finding out these factors. Okay. So, now let us try to see how we can determine them. Other than that, if you look at these equations, there is nothing unknown. Okay. Of course, the temperatures are unknown, which are actually basically you are trying to find out, but other than that everything is material property and the geometry, such as the diameters and then material properties of emissivity and all. So, there is nothing unknown but the heat transfer coefficient between the tube and the cover, and then from the cover to the ambient, which is through wind heat loss factor. So, let us first try to get this heat transfer coefficient between the tube and the cover. Okay. So, what we can do, we can find, so basically what is the geometry? Here we have the tube and here you have the cover with the concentric circle or cylinder rather. So, this is the cover and this is the tube. Okay. And you can see that the area is getting changed as you go towards the cover, area is changing. So, what we can do, we can find an effective, conductivity of the air within the annular area. Okay. So, in that case, if we get that, then we can write that this heat transfer that is happening because of the natural convection, this we can equate it to as if the conduction is happening and an effective value you know. Okay. So, for the heat conduction, you know, when the area changes because of the circular geometry, what you have, the relation is this. Okay. This you have learnt in your conduction heat transfer course. Okay. Particularly this natural log comes because of the change in area. Okay. And here you see that we have used this effective conductivity. So, what we did? We did that we equated this convection term with the right hand side effective conduction term. Isn't it? Okay. Now, the onus comes on us to find out what is the effective conductivity, right, and for that we have to use some standard correlation which has been derived and obtained by rigorous experiment. So, how to find this effective conductivity? Okay. So, the available correlation is due to Rathby and Hollands. Okay. And if you are interested to look at the reference paper, please look at the textbook that we are using, which is by Sukhatme and Nayak. Okay. So, this effective conductivity divided by the actual conductivity, okay, conductivity of the enclosed air is obtained by this correlation. This is the modified Rayleigh number to the power 1/4. Okay. So, here K is the actual conductivity of air at the given pressure, because you also can evacuate this portion, right. So, you can change pressure within this annular space, and that is actually done. You have looked at the evacuated tube collectors while we were talking about the flat plate collector, and here also it is done for the parabolic troughs. So, you have to be careful what is the conductivity at that pressure level, because for gas pressure determines the conductivity value. Okay. And this R A star, it is the modified Rayleigh number. Why we call it modified? Because it is related to the conventional Rayleigh number like this. Okay. So, R A star raised to the power 4, this is related to the conventional Rayleigh number. Okay. And what is conventional Rayleigh number? So, let me write it here first. Conventional Rayleigh number is nothing but the Grashof number multiplied by the Prandtl number. Okay. Grashof number you know for the natural convection, and Prandtl number is the thermal diffusivity and the viscous diffusivity, right. So, that is the normal Rayleigh number. Now, for this case we are modifying it, and here comes the effect of the geometry in the form of natural log of the ratio of the inner diameter for the cover system and the outer diameter of the absorber tube, multiplied by this b to the power 3/4, which I am going to tell you what is b, and d naught to the power 3/5 plus 1 over d c I to the power 3/5, and this whole thing powered 5/4, okay, and that multiplied by the normal Rayleigh number to the power 1/4. So, this is the relation basically between the modified Rayleigh number and conventional Rayleigh number. Okay. Now, here we have introduced this B. B is nothing but the radial gap of this annular space, and this is d c I minus d naught divided by 2. Okay. And of course, all the properties that go into calculation of R A, that means the viscosity, thermal diffusivity, everything is calculated, or rather are calculated at the mean temperature between the plate or tube, absorber tube, and the cover. That means this T p m plus T c by 2, that is the mean temperature between the tube and the cover, and all the properties that you are calculating, that should be at that mean temperature, then only you can find out. Okay. So, Rayleigh number, if you know that, then you go back and find out what is the effective conductivity, okay, and that is how you can find out what is the HPC. So, with all this, the heat transfer, convection heat transfer coefficient between the plate and the cover will be this value K 2 K effective, that means conductivity effective, d naught ln dCi divided by d naught. Okay. So, basically we were after this HPC and H wind, right. We did not know that for the whole analysis, we needed them, and now we know what is the heat transfer coefficient between the plate and the cover. Now, what is left is this wind loss factor. Okay. So, wind loss factor, how to get that? Again, the flat plate collector convection loss correlations won't work here, right, because the geometry is different and all the correlations are strictly or critically dependent on the geometry. So, that is why you need to be careful about using which correlation you are using and where. Okay. So, the correlation that we use, that is due to Hilbert, and that correlation is in terms of the non-dimensional number, right. All the time the correlations are written in terms of non-dimensional number, because you can use it for different size of the same geometry. Okay. That is why it is non-dimensionalized, and that is a function of the Reynolds number to some power of n, and you have a pre exponential function or number which is C1. Okay. So, here the C1 and n are the constants which depends on the Reynolds number. Okay. The range of Reynolds number C1 and n will depend. Okay. So, what are them? So, for Reynolds number between 40 and 4000, okay, we get C1 equal to 0.615 and n equal to 0.466. Okay. For the next range between 4000 and 40,000, we have C1 equal to 0.174 and n equal to 0.618. Okay. And for the even higher range, okay, Reynolds number greater than 40,000, which very rarely you will encounter in a parabolic trough collector. Reynolds number above 40,000 is almost never used. Okay. So, I mean this is the natural convection, right. So, in case of natural convection, going up to that high Reynolds number is typically impossible. Okay. So, that is how you find the HW or the wind loss factor. So, when you know the HP to C and HW, then you will be able to find out the UL and everything else will fall in place, the heat removal factor, collector efficiency factor, and you can find the overall efficiency of the collector, the useful heat gain, all the required quantities you can find. And only one thing is remaining here is to look at how the heat will be transferred from the absorber tube to the fluid. Okay. So, from the absorber tube to the working fluid or the heat transfer fluid which is carrying out the heat. So, now and for that we require the heat transfer coefficient HF. Okay. So, here the typical correlations are available. I am just repeating it because this is a pipe flow. Okay. For pipe flow, you know, for fully developed flow, when the flow is laminar, so usually Reynolds number less than 2000, okay, the Nusselt number, which is the non-dimensional heat transfer coefficient, is basically constant, right. This you have learnt in the heat transfer course for convective heat transfer. Okay. And for turbulent flow, or rather for Reynolds number greater than 2000, we have the well known Ditas-Boelter equation. And there the Nusselt number is a function of Reynolds number as well as Prandtl number. So, this is the pre-exponential factor, and then you have Reynolds number to the power 0.8 and Prandtl number to the power 0.4. Okay. So, these are the standard coefficients from which you will be able to find out what is the HF. Okay. So, here again all the properties should be calculated at the mean fluid temperature, and that is your Tfi plus Tf naught, that means the inlet and outlet temperatures of the fluid, the average of them. Okay. So, that is how we know all the relevant heat transfer coefficient, and the thermal analysis for parabolic trough ends here. Okay. Next thing we are going to look at is the other concentrating collectors. Okay. Parabolic trough and flat plate collectors. Flat plate collector is the non-concentration version, the most common non-concentrated version of solar heat collector, and for the concentrated ones, parabolic trough is the most commonly used geometry. Okay. And we have analyzed it fully from in terms of the optical analysis as well as in terms of the thermal analysis. Now, next thing we are going to look at is what is called the compound parabolic collector. Or more commonly it is abbreviated with CPC, compound parabolic collector. Okay. So, why do we call it compound? Compound because it is not a single parabolic surface anymore, which was in case of the parabolic trough. In parabolic trough, what did you see? We had a single parabola, okay, and you had a collecting tube or absorber tube at the focal point of that parabola. Okay. So, in this case, so this is for PTC, okay, and we had a single parabola. But for CPC, we have more than one parabola, and you can see here that we have two parabolas, and they are actually making up the surface of reflection. Okay. So, before I go into its detail, What is it? It is again a non-imaging kind of concentrator. Then it is also, so we have looked at different classification of this concentrating geometries, right. So, imaging non-imaging was one, linear non-linear or linear volumetric was the other, which is also 2D or 3D. So, this one is non-imaging, this one is again 2D, okay, because you are not focusing on a line, but you are focusing on a plane rather, okay, or rather it is not a point focusing thing, it is a line or plane focusing thing. So, it is a 2D geometry, a 2D concentrator, and the third classification we looked at is the reflector based, right. It is not a refractor based, but it is a reflector based concentrator. Okay. Now, why we use it? Because it has large acceptance angle and tracking requirement, I would say, is minimal. That means, unlike the parabolic trough collector and the other collectors as you see later, where the tracking has to be perfect, it has to be 2-dimensional or rather 2-axis tracking, and the surface has to, or the aperture surface has to track the sun perfectly. But in this case, for the compound parabolic collector, we do not need that. So, that is the particular advantage of this compound parabolic collector, and we will see how it works. Okay. So, here you can see that there are two parabolas, one is parabola 1, okay, and the other one is parabola 2. So, there are two parabolas and a portion of each is included in the reflector surface. So, here you see that from A to B, first let me write what is the reflector surface. A, B and C, D, these are the reflector surfaces, okay, while B, C is the receiver surface or the absorber surface, okay, and AD is the aperture. So, you see that sun rays are coming through this aperture AD and they are getting reflected at, so suppose a particular ray is coming like this. So, it is getting reflected here when it reaches the reflector, and due to parabolic nature of the surface, it will be coming towards the absorber, okay, and similarly for other rays. So, this is the geometry, and here you see that AB portion of the reflector surface is from parabola 1, okay, and DC part of the reflector surface is from parabola 2, is not it. So, the dotted portion here, as you see, dotted portion from both the parabolas, they are not part of the compound parabolic collector. Okay. Now, another thing you notice that this point C, okay, C is the origin for the first parabola. So, C is the origin for parabola 1 and that origin lies on parabola 2, right. C is part of the parabola 2, but it is the origin of parabola 1. Similarly, B, it is the origin for parabola 2 and it lies on parabola 1. So, that is how both the parabolas are interconnected. One's origin is part of the other's surface, okay. And this is the two-dimensional cut that we are seeing. So, two-dimensional section we are looking at, and the actual collector is going into the board perpendicular to the surface of the board, okay. So, perpendicular, okay, let me write in the next slide. So, the actual surface is perpendicular to the surface of the board, okay. So, this is very interesting geometry, isn't it? These two parabola are interconnected and the common part you are taking as the reflecting surface, okay. Also note here that the axis of parabola 2 is which one? Axis of the parabola 2 is this line, right, okay, and that is parabola 2 is parallel to this CA line. CA is what? The connector between the C is the origin of parabola 1. So, this is the origin of parabola 1 and the edge of aperture AD, and A is on parabola 1. So, that is how this is connected, okay. So, axis of parabola 2 is parallel to the connector between the origin of the parabola 1 and the aperture edge which is on the parabola 1. So, aperture AD, edge of aperture AD which is on parabola 1, okay. And similarly you have axis of parabola 1 is parallel to BD, isn't it? B is the origin of parabola 2 and D is the aperture edge on parabola 2, okay. And here you also notice that the tangents, so tangents at the aperture edge or rather aperture edges which are at A and at D, they are parallel to the axis of CPC, okay. So, this is the axis of CPC, right, you see, and if you draw a tangent here at D which will be like this, and at A which will be like this, both this one and this one, these tangents will be parallel to the axis of CPC. So, thus this geometry is symmetric, and it is very interesting because now you have a acceptance angle which is much larger. So, let me write it here. So, the acceptance angle is this 2 theta A that you see in the diagram. That 2 theta A, how you are getting? It is the angle AED. Okay. An acceptance angle, we have talked about it earlier. What does it mean? It means that you have the, even if the aperture and the sun rays are inclined to each other, they do not have to be always normal. If they are inclined to each other and that inclination angle is within this 2 theta A, then that particular sun ray will actually reach the receiver. That is the concept of acceptance angle. Okay. So, even if the surface, or even is the aperture surface is inclined to sun rays, and the angle of inclination is within this 2 theta A, which is the acceptance angle, then the ray will reach the receiver surface. So, that is very interesting because in that case you can say that okay, if some sun ray is, so if you increase this angle, now if some sun ray is coming like this, oops, okay, let me use another color here. If sun ray is coming like this, okay, and this is your aperture plane, and you can see that it is not normal to the aperture plane, but still it will hit the reflector here, and it will, maybe it will have multiple reflection, it will be reflected back again, and the sun ray will actually reach the receiver. So, that is how this angle of acceptance is increasing your range for which the rays will be accepted and it will reach the receiver. So, that is why CPC does require minimal tracking. That is why it is called minimal tracking. It can accept non-normal incidence effectively. Okay. It can accept non-normal or inclined incidence effectively. Okay. And often the compound parabolic collectors are not fitted with any tracking mechanism. It is not possible to go in detail of compound parabolic collector in this course, but it can be shown that for the whole year you can fix a particular position of a CPC and you can get effective concentration up to 4-5 and for 8 hours a day, that is possible without doing any tracking. Okay. So, that is the beauty of it. Okay. Now, if we try to analyze it in more quantitative form, then what we can write, let us say that this AD is our width of the aperture W, okay, and BC, which is the width of the receiver B. Okay. So, the concentration ratio that we get here is W by B, right, the aperture area divided by the receiver area, that is the concentration ratio we are after. And so, it can be shown that this W by B is 1 over sin theta A. Okay. So, 2 theta A is the acceptance angle and theta A is called half acceptance angle, half acceptance. Okay. So, this can be shown, and for parabola 2 we have this xy coordinate system. For parabola 2, look at the figure, we have this xy coordinate system. Okay. And from there what we can write, this y is equal to x square divided by 2b 1 plus sin theta A. Just from the equation of parabola you can write this. Okay. And the focal length is OB. So, OB is 1 plus sin theta A multiplied by B by 2. So, this you can find. So, now for segment CD, which is on parabola 2, you can write the coordinates. For C, the x coordinate is b cos theta A and y coordinate is b by 2 1 minus sin theta A. Okay. And for point D, the x coordinate is b plus w cos theta A and y coordinate is b by 2 1 minus sin theta A multiplied by 1 plus 1 over sin theta A squared. Okay. So, once we know the coordinates of C and D, what we can write? So, whenever we know the coordinate of C and D, we can write the height to aperture ratio. Okay. That will tell us how much reflector surface we will need and all, right. The geometry if we want to find, then we need to know what is the height to aperture ratio. So, that is h divided by w, that is half 1 plus 1 by sin theta A cos theta A, and you can write it in terms of the concentration ratio itself, because concentration ratio is 1 over sin theta A, right. So, 1 plus C, and this cos theta A you can write in terms of sin theta A by 1 minus sin square theta A, and that is how you can write this as the concentration ratio. So, this you can see here that this is a function of concentration ratio only. Okay. So, whatever concentration ratio you want, that will determine what will be your half acceptance angle and what will be your height to aperture ratio. Okay. Now, another important quantity is to know what is the area of the reflector surface. Okay. Area of the reflector surface, why it is important? Because the reflector surface is where you are going to put the reflecting coating, and which is the most costly thing in this whole arrangement. So, you have to use the super reflector and which will stay for long time. So, that coating, how much of that you will require will depend on what is the area of the reflector surface, and that is why it is known. It is important to know. So, let us say that is area of concentrator or reflector, okay, A con, and that A con divided by W into L. L is the length perpendicular to the board. So, that one you can write, or it can be shown So, L, let me write L is the length perpendicular to the direction of the board. Okay. So, this expression is theta A plus natural log of 1 plus sin theta A 1 plus cos theta A divided by sin theta A cos theta A plus 2 plus 2 sin theta A to the power half, that means square root this whole thing, okay, minus root 2 cos theta A divided by 1 plus sin theta A to the power 3 by 2. Yeah. Okay. So, this is the long expression, and we can simplify it significantly. So, if the concentration ratio is less than 3, okay, then it can be shown, that this A con divided by WL expression becomes very simple, not that long, but just 1 over C. Okay. So, we will see from here in the next class. Thank you.